Good day, everyone. I am Sarah Vera M. Shapir, and again, my geometric model is the BoomSun prism. And after our four projects, we're now down to our fifth project or fifth presentation, which is we need to show that our figure is a permutation group. So, So the BoomSun prism is a geometric model based on an octagonal structure. It has 8 points labeled 1 through 8 on both its front and back faces. And as we can see here, and it says here that we need to let 1 is equal to 1 is to 1, and so on and so forth. And we have here, let beta be the permutations for rotation and sigma be the permutations for line symmetry. So each symmetry of the prism can be expressed as a permutation. That is rearrangement of the points, and we define them just like what I've said, the beta and the sigma. So we have here the movements for the permutations for rotation. So for the first one is B sub 0, which is do nothing or the identity element. And then B sub 1 rotates the prism 45-degree counterclockwise. B sub 2 rotate 90-degree counterclockwise. Rotate 135-degree counterclockwise. B sub 4 is rotate 180-degree counterclockwise. B sub 5 is rotate 225-degree counterclockwise. B sub 6 is rotate 270-degree counterclockwise. And B sub 7 is rotate 315-degree counterclockwise. Now, we have here are the reflection permutations. So for the first one, which is O sub 1 or sigma sub 1, is flip through vertical line, and then sigma sub 2 flip, then rotates 45-degree clockwise, so on and so forth. So we have here is the permutation for each element. And as you can see here is our B sub 0 is 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, because like what I've said, it is the identity or do nothing movement. So from the combinations we had here, from these movements, we have here the results from B sub 0 until sigma or O sub 8. Okay? So to prove that Z is a permutation group, we need to verify the four group actions under composition. So the first one is, so here's the table of for our or the permutation table with operation under multiplication. So let's see if it is closed. Every composition of symmetries result in another element of Z, meaning it is closed since all the resulting elements are in the set. Now let's identify the identity element. So the identity element here is the sigma 0, and the inverses are here where we can find the identity element. Check the associativity. We need to flip the table, and when we exchange the rows and columns, it will result after exchanging the rows and columns. And as we can see, by exchanging the rows and columns, the resulting elements on the flip table can be arranged like on the original table. Therefore, we can conclude that it is associative. Therefore, this permutation table also forms a group under permutation multiplication because it satisfies all the conditions. So now let's combine each um, permutations on each other. So here are the results. I don't need to. I won't elaborate it anymore because this was to take so long. But for instance, we have here sigma sub 0 is equal to sigma 0. And if you combine both the identity element, therefore, it will only result to the identity element. Let's see. Um, Sigma sub 0 is multiplied to sigma sub 1. The result is 1, 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 1, which is sigma sub 1. Let's see it on the table if it's the same. 0. So, very. Therefore, our answers are correct. So basically, that's how we can get the permutation of a group. So I won't explain this. I won't explain all of this anymore because it would take so long. But when we are combining two or the multiplying two, this permutation, we will always need to start at the right part first before and then multiply it to the left one. So that's it for the permutation.